Welcome to part 2. Let's continue where we left off. So let's see question 2. So we're going to start with question 2 now. So question 2, obviously going to have 2.1. Okay, this is all 2.1, right? So 2.1 is going to be labeled with letters, right? From A to whatever letter that is. So if we read the following information, complete the following code in which a generic, you see, the keyword is generic, Q2 cube class acts as a container for a three-dimensional data type of type T. So there's 3 pointers. I'm expecting three, yeah, 3 pointers here, but they didn't. It's a question that you also had to answer, but yeah, make sure you always read that first statement here. It gives you more information about what's going on. They said it's generic. Remember the way we make generic, something generic. It's either a generic function, a generic class, a generic record structure, anything generic. You use the templates, right? So the answer for A, remember that the template, in order to make a template, you have to say template to say it's a template, and then it's going to take in some type name called T, right? But then when you look at the question paper, there's already from this from the less than symbol up until the end, we already have that information. But then there's something missing behind the less than symbol. If you check this, what's behind the less than symbol is the keyword template. So that's what's missing here. So I'm gonna put template as my answer for A, because that's what's missing there. So A is going to be the keyword template. Um, okay, okay, now it's fine. So gonna say template, and then this, let's see. So I have a class, generic class, right? Q2 cube as stated here. And there's B. I need to fill in B. If you check this thing, it looks like a function, but it is the same name as the class. So obviously this is a constructor and a default constructor. This is a parameterized constructor because it has parameters. And I don't see a reference there, so it's not a copy constructor. It's a parameterized constructor. And then I get to another uh, thing that looks like a function and it has the same name as the class. Therefore, it's also a constructor. And then I see the reference and the const, then I know it's a copy constructor. And then I see operators, and then I see everything. And then I see the private keyword here. But then, as you can see from already these three constructors, you can tell that the answer should be public, because the constructors need to be public. Because remember, when you initialize the object, you have to take information from the user. So you have to make it public. Everything from, and you always start with the constructors. So we know the answer for B is going to be public. So the answer is going to be public. That's what the answer is going to be. And then let's see the next one, C. You can see this is a copy constructor, right? Now, this is a very tricky thing. You might be like, okay, but then there's nothing missing here because it's a const reference though, Q2 cube reference. But then if you remember, it's a template. If you remember what they said, it's generic. Generic, you know that every time you pass in an object of this type, you must specify a type within this less than and greater than symbols, because that's what it means when you're writing the template at the top. When you do this, right, what you're saying is that this class is going to take in some type within these brackets, within this less than and greater than symbol. So therefore, every time I instantiate the class, let's say, for example, the class is A, it's called A, right? So whenever I create an instance of A, I must always pass in a type there. As you can see, it supports me, it knows what I'm talking about because it knows that this is generic. What type is going to be of type int, like this. That's what this means. It means that it's going to be generic, and then the type is going to be passed within these two symbols, the less than and the greater than symbol. So since that's the case, it means that even when I'm creating constructors, copy constructor to be exact, I also need to do that because it's taking in a Q2 cube, and Q2 cube is generic. If you check there at the top where I've highlighted, it's generic. So what's missing here is the less than, and remember the type name, they've called it what? T. And they even tell you here, that's what I like. They even tell you, you don't even need to read this first line. They even tell you it's of type T. So you know the template is going to be of type T. So what's missing in Q2 cube? It's the less than, and then a T, and then greater than symbol. So to state that it takes in some type called T, any type, we're just going to call it T for now. Okay, so I've reached the end there. So I'm going to say D, then D, let's say. We have an accessor because you see we're getting X size. If you check the variables here, there's X size. It's a private member variable, and it's under the public because we've already filled in the public. It's under public, it's a public function, and it's called get X size. Remember, if it's prefixed, if the first word is a get, you know it's an accessor. But if the first word is set, then you know it's a mutator. It's a setter. So remember when you're getting a value, right? You want to avoid changing the value. You can't change the value. You're just only meant to have access privileges, not modification privileges. You can only access, not modify it. So if you can only access and not modify it, that means at the end, I need to put a const there to state that this function, it takes the value in a constant manner. It doesn't change the value. So the answer for D is going to be const because this is an accessor. It's only meant to get the value. Shouldn't change the value. So I'm going to put const there. That's the answer for D. And then E, it's the assignment operator. So with the assignment operator, right, as you can see, what I like about these people, they sort of, if you're really smart, you can get the answer. Look at this one, const cube parameter reference exactly as this. So if you actually saw it here, you would know that that's what's missing there. Remember the assignment and the copy construct is exactly the same syntax. The parameters that they're taken is exactly the same. Const q2 cube by reference, and then the only difference is that you're going to call it object right hand side because this is an operator. It does an operation based on two operands on the left hand side and the right hand side. So we have that. This is an operator, it's assignment operator. So I feel like based on how they taught you guys, you should always put that const there. Remember that I'm supposed to assign taking an object from the right hand side and assign it to myself, right? And then return, and then return, my updated self. So in order for me to return my updated self, I must return it by address. Remember, so that it makes things faster. Because if you remember an operator, right? If you remember an operator, you you have a value from on the left hand side, and you have the operator in between. So here you're gonna have an operator, and here you're gonna have a right hand side value, right? So for example, x is equals to 9. So the left hand side is x, right hand side is 9, the operator is equals to. So remember what the assignment is supposed to do. I'm supposed to assign a value to the current variable so that in such a way that whenever I say cout x, right, it outputs this value. It outputs the value. but then that value that it's outputting, it should be a constant, right? So it should be a constant, and then the variable, whenever you want to change it again, you can reassign it again. But then whatever the return value is going to be, is going to be a constant. So with that being said, it means that I'm going to have an operator, right? Assignment, right? Which takes in an object. It takes in in our case, it's what? Q2 cube, right? Q2 cube, right? It takes in an object. Let's call it object right hand side, because it's going to have, I'm taking the value on the right hand side, then I'm going to assign to myself. That's why I'm calling it object right hand side. But then remember, it's only assignment. I'm only copying the value. So since I'm only copying the value, I'm going to put a const in front to say this object shouldn't be changed. You should just only copy the value. But then to make it faster, I'm going to copy it by address. I'm going to take the address like this so that it becomes faster. I don't get the whole value. Let's say the object is very big. It's like 13 gigs. I'm not going to copy the whole 13 gigs. I'm just going to go to where it's located, its address. So you can, this whole thing of operator and addresses and all of this is what it means. So imagine there wasn't like any convenience like having to type eve.uj.ac.za. Imagine there wasn't this convenience, this address, it wasn't there. In order to run Eve, imagine in order to run Eve, they had to send you the zipped file of Eve. Then you double click on that zipped file, you unzip, then you double click on the file. It could be .aspx, .html. It's an HTML file, whatever that file is, and then you run Eve. Imagine that was the only way to run it. And imagine how big of an institution UJ is, and imagine how big the information that it has, the amount of students and all of that information. With that being said, that means you're gonna have a very big file. So imagine having a big file like 90 gigs of space. Imagine every time you want to run a website or get something, you'd have to download the whole thing by value and then run it. If it's very big, you're gonna have issues, and you're gonna have issues if you have a very limited amount of memory. So in order to avoid that, we work with address. You see, this is an address. You go to eve.dj.ac and then you have the website. There it is. I don't have to get it by value and get the files and get the images and get this physical image. I don't have to, everything is running on a specific address. So it becomes faster. You see, what I have to do is just say if, let's do this again. What I have to do is just say if, you see, and then I press enter. Look at how fast that was. Because I'm using this address. I'm not getting the files, the values and everything. I'm not getting all of that. So that's what we're doing here, taking it by address. But remember, this is a templated type, so you must pass by T there, add some type in between the brackets. And then remember that after assigning this value, right, X is going to have a returned value. And whatever return value it is, it depends on the type of what's on the right hand side. So I'm assigning it to a Q2 cube of this type, right? This is what I'm going to have to return, right? It's like, for example, like this. Imagine this is like this: int x is equals to 9. Obviously, this x value must return an integer. It can't return a double. It can't miraculously assign an integer and return a double if it's of type int. It can't do that. So that's what we're doing here. I'm taking in a value. You can imagine this parameter here. Okay, let me just show you in terms of integers how it would look. So imagine we have this class int, right? And then we overloading assignment operator, right? So assignment operator, it takes in an integer in constant form, and we take it by address. And then I have obj right inside, and then I return an integer, but then I want to return an integer by address. And then I also want to make sure that that integer that I've returned, it shouldn't be changed. If you want to change, you just have to reassign it, right? So I was going to put that const there at the end. So there we go. There's our operator, right? So in terms of this line of code, what would happen if I do this? What's going to happen is that it's going to take in 9 as the input here. And remember, I won't take 9 as it is. I'll take its address where 9 is stored. Because if you remember, I'm taking an integer by address and I shouldn't change it. That's the const. So it's going to take in 9 here as the input, like this. And then it's going to assign it to my current instance of the class. In this case, it's X. And then return that value that I've returned myself, return the address of myself, and make sure it's in constant form. I can't change that value that I've assigned. So in a way, this operator can be broken down into this. And assume it's basically saying X. Remember that this operator, what it's also a function. So I can also do it like this. I can call this and say dot operator equals to 9. Right? I can do this. But then C++ has introduced a better syntax for this, the normal mathematical way of doing it, the way you see it. Instead of calling the function, you can just put that operator as it is like this. And then you see now this makes much more sense. But then you can literally call it like that. Let me just show you as an example. So remember, this is supposed to return that value, and you shouldn't be able to change it after returning it. So let's do a simple example. I hope it allows me to do so. Let's set it to X, right? And then I'm going to say X dot. I want to see. Hmm, okay, so it must have a class type. Okay, I see. So I can only demonstrate this example only in class when we've created our own class, because yeah, I remember these data types and they're not really classes, but I just use a class to simplify, to show a similarity of it. It's similar to that, but it's not really behind the hood. They are not implemented as classes. So let's just make a simple class, right? Let's call it integer, defining my own type of integer. It's going to have an operator. So it returns a const integer by reference, right? And then the operator that I'm overloading, it's assignment operator, basically operator equals to. And then it takes in the same type as my copy construct. So obj right inside. And then there we go. And remember, there's going to be a deep copy, perform a deep copy. So what I'm going to do is private, then let's say int um, int num, initialize it to 0, whatever that value is. So let's perform the deep copy. If you have dynamic memory, in our case, we don't really have to worry about that. What I'll just do is I'll just say num equals to obj right hand side dot num in just simple terms, right? And then remember, I need to return myself. So how do I return myself? Return this dereferenced like this, right? So I have that operate. So let me show you what I was saying about the syntax. So I can have integer a, right? That's the first integer. Then I can assign it to a new value and say a is equal to 90, right? There's the, okay, why is it? No operator matches this. Does not match parameter. Oh, okay, I see. So I need to take in another integer. Yeah, my bad. So it must take in an integer like this. Yeah, and then I'm just gonna say that, yeah, it's a bit complicated when you have to do it like this, but yeah, it takes in another integer, right? Like this. Let's not work with objects for now. Let's not worry about objects because since I was taking in an object, remember. So that's why it was complaining. And then here I'm passing an integer. So it tried to check what am I passing here. It saw, oh, this is an object. And then it's expecting an object, but I passed 90, which is an integer. So that's the first way. This one is the first way to assign it. And then the second way is to literally say dot operator equals to, and let's say it's equal to 200 like this. This is the second way of doing it. You see, you don't complain. But then this is very similar to maths because you see the syntax, it's like understandable. Imagine having to write it like this. It's going to be very confusing, but it still does work for both in both ways. So I'm going to say output, okay, I shouldn't say, oh, okay, yeah, it's fine. So output, okay, output a.num. But remember the num is public in line. So this is before, right? And then, oh, it's I made it private. Let me make it public. And then I output the very same number, calling the operator in a different way. Okay, G plus plus. Okay, that's a very long name that I gave it. Exam 2021 underscore memo .cpp. Where did I store it again? Under documents, right? It can't find it because it's not here. Should say cd. Where's the, okay, there it is. So it's changed directory into computer science 1B 2021 memo. So I want to move to that folder and then list. Okay, there it is. There's the file. So G++ create an object file where it's going to have the binary code and then call it exam. Right, simple. And then dot forward slash exam to execute it. As you can see, it does change 90, 200. It does work. It does change the value. But then the problem is that the syntax, the second way is a bit confusing. But I just wanted to show you that this is also how you can call it. But then this is a more natural way of using it. But it's still a function. As you can see, it's function. And it's a function that's part of the class. As you can see, I'm only calling it after I've created an instance. So it's part of the class. So this is how the operator is going to be if we're working with our own custom integer. But then we're working with our own type. So it's going to take in a cube by reference, and then it's going to have to return a Q2 cube by reference. Because if you don't return the value, then okay, how are we going to output the value? So we need to return the value and then make sure it's returned in constant form. You can't change it. So this value that you're going to output here, you can, how do I put it? You can't change the value that's returned. So 90 is going to be the value that's returned. You can't change 90, but you can reassign A to a different value. Notice the difference with what I said. So here, what's missing is const. It's basically from here, from const up until this address of. That's what it's supposed to return here. So E just going to be const q2 cube type T address of F. Okay, let me see. Okay, 25 minutes have already passed. I need to be a bit faster. Let's see. Oh, so it's the invocation operator, right? Oh, no, it's yeah, I think it's called the invocation. But basically it's the indexing. You're indexing and getting a value into the array. Remember what they said at the top. It's a 3-dimensional data type of type T. They said it's of type T. So obviously I must return T reference. Remember, what is return a reference to make the application a bit faster, or fast in simple terms. So what's missing here is just a T. So T reference. So what's missing there is a T because my array is of what type? Type T. So if I'm indexing, obviously I'm expecting to get back a T, a value of type T. And G, okay. Then G, where's G? Okay, there's G. We can see it's of type T and it's a cube. It represents the cube. So basically this is our 3-dimensional array that they were talking about. If you check here at the top, they said 3-dimensional of type T. So I have to create 3 pointers. Because remember what I said, we can use each pointer to sort of like store the dimension in each pointer. So the first dimension can be represented by the first pointer, the second dimension represented by the second pointer, the third dimension represented by the third pointer. Each pointer sort of like represents a dimension. So if they say 3-dimension, in simple terms, they mean 3 pointers. 2-dimension, 2 pointers. 1-dimension, 1 pointer. In this case, they want 3-dimension. Remember, be careful of the answer that you write. Only provide the missing information. They said type T here. T is already there. What's missing is the 3 pointers. So the answer for G is going to be 3 pointers like this. Okay, there's still more. So what is H? This is the implementation of the assignment operator. Remember how we implement the assignment operator. The way we implement the assignment operator is that, yeah, they made a mistake in this code. They are copying themselves. You see, there's a huge mistake here. It's supposed to pass in that object to copy that object's values to myself. But here they're passing this. So you're copying yourself. So it's like saying X is equals to X. That's what they're doing here, which is very wrong. They made a mistake here. They didn't see, but yeah, this is a mistake. So if this, remember this stores the address. If this, my current, if my address, remember this stores the current instance. If my address is dash address of the other object, what's going on here? Remember what I said, I want to avoid reassignment. So if, for example, I have, let's make a simple example. I have A and B, right? And then let's say A is equals to 10, and then B is equals to 10, right? And then let's say I want to, okay, let's use C. I've already declared variable named A. So let's use C. So with C, let's say I want to change C's value to be B's value. But wait a minute, these things are the same value. So in order for us to avoid having to reassign, that's why we check the addresses. And remember, addresses make the application faster. So before I do all of this, before I assign the value of C to B, I check if the address of C is not equal to the address of B, then I can assign. So if the addresses are not pointing to the same address, then I can assign C to be B's value. That's how we do assignment. Because remember, with objects, they get stored. If you assign an object to another object, they store the same, basically they point to the same address, right? So in order for us to avoid reassigning something that's already reassigned, some people think that is already equal, that are already pointing to the same address. I mean, I must make sure that the addresses, they are not pointing to the same address. So my address is not pointing to the same address of this object. So what's missing is not equals to. I need to make sure my address is not pointing to the address of that object that I'm trying to assign to. If they are not equals to, then I can do this. I can do this assignment. So H is going to be not equals to. I need to make sure my address is not equal to the address of what I'm taking in. Then remember the format of uh, implementing the assignment operator. You need to deallocate memory first, right? After deallocating, then you set up the queue, you allocate memory. After allocating memory, and then you copy. Because why am I doing so? Because the objects could be of different size. So that's why I need to delete memory of myself, and then set my memory to be the memory, this to be the size of this object that I'm trying to copy from, so that there's no memory leakage. Imagine you have a glass a glass or cup that's like 500 milliliters, and you have 2 liters of Coca-Cola, and you want to pour the whole 2 liters of Coca-Cola into the glass. That's not going to happen. There's going to be an overflow. So in order to avoid that, I make sure my container that I'm trying to pour into, it's the same size as the thing that I'm taking from. So if I'm taking from the 2 liters of Coke, therefore I need to make sure my container is exactly the same size. It's also 2 liters. So that's the whole point here. But in order to make sure that's the case, I deallocate first. I remove whatever memory is there. By deallocating, by deleting, it means that throw away that 500 milliliters glass, throw it away. Take and then set up cube, it's allocating memory, right? Which basically means take a container that's exactly the same size as my object. That's why I even passed the size of that object, because I want a container that's exactly the same size as the size of the object that I'm trying to copy from. Once that's done, I've allocated memory. They are the same size. They're both 2 liters. Then now I do the copying. I take from the 2 liters of Coke into the empty 2 liters and transfer, because they are all equal. They're both 2 liters of Coke. So I can say 2 liter Coke. Let's say 2 liter Coke, right? So you can see the 2 liters, right? Because I feel like we're not all the same. We cannot all picture things. So I feel like it's best to also show images. So as you can see, this is the 2 liter of Coke, right? This 2 liter of Coke. Uh, let me see if it's going to open. Yeah, there we go. So you see this 2 liters of Coke, right? It's 2 liters. So it being 2 liters, if I want to transfer all of the contents of this 2 liter of Coke, if I want to transfer all of them, I need to make sure my other container is also 2 liters. So I'm just going to say empty 2 liter Coke like this. Let me see. I want it empty. Hmm. Okay, let's just use this example, because this one shows sort of like a drawing of, yeah, this is what I wanted. Yeah, so you can see we need to make sure that these containers are the same size, right? So if I want to transfer this Coke into here, I need to make sure they're the same size. So if you check our code, how do I, let's say, what happens is that we assume that we don't already have something that of that size. That's the first assumption. What do I mean by that? We delete whatever memory is there. We're assuming that they are not equal. The containers are not the same size. I delete, I get rid of that container. And then I set up, or I create another a container that's the same size as my object. So basically I call I construct another object. Remember, constructors are builders. I build an object that's the same size as my object right hand side. After building, this is what you're going to have. There's the object now. It's the same size as this one. You've built the object. It's the same size, 2 liters, 2 liters. Then now the last part, copy the cube. So I'm transferring from this. That's why I'm saying they made a mistake here. You're supposed to pass in an object right inside, the thing that you're copying from. So I transfer now. So now you can imagine, you see this arrow, you can imagine this cold drink is open, is being poured inside this empty container, because now I'm sure they are the same size. You see 2 liters, 2 liters. They are now the same size. So therefore, what's missing is the deallocation, because remember what I said, we start by deleting. We assume they're not the same size. So I need to start by deleting. Let's go and check. Where's the one for deleting? There's the helper function, free cube. It's always the one that has no parameters, because remember, a destructor has no parameters. So it's always the one with no parameters. So it's called free cube. So what's missing in that line in I is basically free cube. So free cube and the semicolon. Remember, it's you're writing the line of code there. They won't penalize you, but just for the sake of showing you understanding, make sure you put the semicolon there, because you see all the other lines have semicolons, right? Remember, semicolon is like a full stop in a statement. Every line of code that you write in C++, it's interpreted as a statement or as a sentence. So you need to show that this sentence ends here by putting the semicolon. The semicolon is equivalent to a full stop in English, which states that this statement ends here. This sentence stops here, so that it doesn't continue reading all the other ones and think, okay, the statement hasn't ended yet. That's why I'm saying it's important to put that semicolon. And then remember, I need to return myself. After updating, I need to return myself dereferenced. Because remember, this operator stores the address. So I need to return hij. So I need to return myself dereferenced. Yes. Because remember, this is the address, right? And then remember, pointer means point to or go to that address. In this case, it's this address, my current address, the current instance. So we are done. We're gonna go to 2.2 now. Yeah, time sure does fly. So, okay, but I have to finish question 2. I feel like each video should represent a question. And then the next video we do question 3. Then the last one we do question 4. And then done. So we have 2.2. Okay, let me drink some water. My throat, I'm parched. Uh, okay, let's continue. The copy cube function assumes that the current object is already the same size. Yeah, that is being copied, which is true. That's why we had to deallocate and allocate and make it the same size. Because this one, when you call it, it assumes they're the same size. That's why it's called a shallow copy. It's very shallow. It's assuming things when it shouldn't assume. Whereas this assignment operator doesn't assume anything. It starts it deletes everything and allocates everything the way it should be allocating, and make sure they're the same size before you copy. And it also makes sure you don't copy something that's already that's already copied. So you make sure the addresses are different before you try to copy. So this statement is true. The copy cube function assumes that the current object is already the same size as the object that is being copied, which is true. If this is not the case, then an error condition has been encountered. That's true. So provide simple two-class hierarchy consisting of a base exception and a specific exception type of this kind of error. So what error? How can I name the error? So basically what they're saying is that you must create an error, you must do exception handling for the copy cube, the copy construct. And remember that it assumes that they're the same size, right? So basically what they're saying is that if it happens to not be the same size, that's what they mean here. If this is not the case, if it happens to not be the same size, then an error condition has been encountered. So an error. Okay, yeah. I'll just call it, there's a special name for it. I can call it bounds. Let me see. Yeah, because we're dealing with an array here. We are indexing. So obviously what's going to happen is that I'm going to try to index into an index that doesn't exist, especially if the object that I'm taking in is bigger than myself. And remember, the copy cube assumes they're equal. If it happens to be bigger, it's going to keep trying to index and index, and then it happens to be out of bounds, right? So let me show you a simple example of this. Out of bounds exception. Out of bounds, basically, you went out of the range. Bounds means range. We went out of the range. And that's it's a type of exception that describes you going out of the bounds or out of the range. What could be the range? Let's create arrays, right? So I'm going to create an array, call it array 1, then allocate, let's say it should store 3 integers, right? Simple. And then I create another one, array 2, which should store 5, 5 integers, right? Simple, right? Straightforward so far, right? Now let me initialize them to their default values, right? Let's say this one's gonna have zeros everywhere. So I'm gonna use the list initialize. If we leave it empty like this, it's going to initialize every value in that container to 0. And then with this one, I'm gonna specify all the values. So it's going to initialize it to 3, 19, 8, just random values, 42. See, we have 5 integers, right? And remember, this is the first integers at index 0, index 1, index 2, index 3, index 4. That's how it's going to be stored. So now let's try to copy. Try to copy. Remember, the copy constructor, it assumes they're already the same size. Now I'm just going to use this with the assumption that they are the same size. So I is less than 5, right? Because the size of what I'm trying, the size of the array that I'm copying from, this is the array that I'm copying from. Its size is 5. So I'm going to take that size. Then I say array 1 index I is equal to the array 2 that I'm copying from, right? Should be fine, right? That's what we assume. Let's see what the issue with this. Now you understand why it's called the shallow copy. It's so shallow because it's assuming a lot of things. It shouldn't be assuming things. So let's run it. E++, okay. I have to change. I shouldn't have exited. Now I have to change directories. And ls and then cd, the folder called computer science 1b 2021 memo and ls. So there's the file. So okay, there's the object file called exam there, but I need to build it again. So g++ exam underscore, and then I'm gonna press tab so that it finishes for me. There we go. I don't want to type everything. And then I give it a name, the object file exam again, then dot / exam. There should be an error, but it's not raising the error. I don't know if I should open it inside. I think I should. I don't know, but I don't know why it's not raising the error. It should raise an error. It definitely should be raising an error because I did save out of this though. Let's do it again. It's not even raising an error. So what I would do, right? Let's make it just a 1 integer and see how it will play out now. Doesn't complain. Well, it should complain. I think it's because this is just an let's try it inside code blocks. This is the only code that I need right here. Let's try it inside code blocks. because I think the issue is that I'm using VS Code, and VS Code is just a text editor. It doesn't have all of the tools that you need to write C++ code. Um, Let me change perspective to minimal. Okay, so I'm gonna need to close all of this. There we go. Then, yeah, this should raise an exception. It's not complaining. I don't know why it's not doing that, but it should be raising an exception. Because, why am I saying so? Because this, remember, I'm using the same I variable. It's going to keep indexing, and then it's going to index out of the bounds. I don't know why it's not picking up that error, but it definitely should be picking up that error. I think it's because the VS Code one also, it's incomplete. I think if you try it, or if you guys try it on your code blocks, since everything is installed properly, then it should work. Yeah, I'll try to fix my code blocks to make sure that it runs properly. But yeah, that should be an error. So what they said here is that you should accommodate that error. I was just trying to show you what type of error can happen. Remember, you can only store one value. So what's going to happen is going to start at index 0, right? Which is correct at this point. And then now it's going to look for index 1, which doesn't exist. So now it's going to be out of bounds. So it's going to go out of the bounds of the array. So they said you should create a class inheritance hierarchy to represent that, which is basically simple. So you always have the ancestor class, which is the exception, right? Um, Going to be like this, and then you're gonna have the child classes out of bounds exception. And then it's going to inherit from the exception ancestor class like this. So this is how they wanted you to answer that question. So this is the answer for that question. So whenever they say class inheritance hierarchy, always start with the ancestor class, which is just exception. And then you're going to have a child class. The child class always has the suffix exception at the end, which basically which basically states what type of exception it is. So if you write like this, it's perfect because you know that this is an out of bounds exception. So that's the answer for 2.2. Yeah, I'm just gonna leave it like this. Let me see. Mm, Okay, let's copy it inside Notepad. Okay, copy it inside Notepad and then copy the code here. And then I'm gonna use, I'm supposed to use, is this blue? Okay, yeah, I'm just gonna use that blue. And then here I'm gonna use sort of like a green so that it's a bit clear what's the class name. There's a bit of color in it. Then this one's going to be blue. Nope, this blue. There we go. So you see, you can tell that this is gold. I'm just adding a bit of color there so that it shows that this is gold. Um, so which defines this type of error, right? Provide the code for the two class hierarchy. It just to create two classes, basically. That's what they mean. And we did create the two classes. and then write code to protect the following using exception handling. So we need to protect this code using exception handling because the objects might not be the same size, right? So basically I must use what I've created in that previous line, though that class hierarchy that I've created. So this is how you do it, right? If you remember, you say you try some code and you expect you expect it to throw an error. If it throws an error, you catch the error. And remember the way we catch the errors, right? Start by the child classes first. So out of bounds, exception like this, EX. Okay, out of bounds, EX like this. And then you always catch that generic one at the end, which is just exception EX like this. So here you can just output something simple. You can just say standard CR. Then you say objects are not of the same size, or objects should be of the same size. Then here you're just gonna it's just a general exception. You can't really tell what exactly the exception is. So I'm just gonna say some exception occurred. Just some exception. Just some exception. And then for the sake of it looking good or looking like code, I'm gonna color it in certain ways. So this is going to be that green here, and this is going to be that blue here, and then this one, yeah, I'll just color it green or blue. Let me just color it blue like this. Yeah, that's a bit better. There's no need for me to do this, just that I want it to be clear when you're looking at the code. There we go. Yeah, you can tell, okay, yeah, this is code 2.4. I'll find a clever way to fix this, but I'll see, because I can't be changing colors over and over and over. Over there, I said the catch, it's also gonna need to change color to be blue. Yeah, so objects are not the same size. So we are not done. We need to put the code that we are trying here. Put the code. Here, this is where the code that will throw an exception. Let me see. Did I say protect? Let me see. I think I'm not. Oh, okay. So they say assume that it has been updated to raise the exception. So assume that it's been implemented. So they checked if the objects are the same size or not, and then it threw an exception if they are not the same size. So just assume that happened. So we have the code. So just assume they wrote the code for you. So all I have to do is just put all of this code inside the try. That's it. That's all I have to do. You're always going to do this because this is the code that you're trying here. What's going to happen is that when you try to assign or call or copy or whatever, it's going to assume that they're of the same size. So you need to make sure that they are it throws an error, it places inside the try because it might throw an error, right? So let me see if, okay, now it won't work. But I must find a way to write that code. So Q2 cube. So I create an obj cube of type int, a Q2 cube of type int called obj cube 345. Okay, Q2 cube type int bj cube 6 and 3 4 5 parameter, and then I'm going to create a qt cube, type int again. This is going to be called obj copy. Then I copy from obj cube. I think that should be how it's structured. Yeah, I copy from obj cube. So this is the code, right? So I must try this code because it might, this part, especially this part, this might raise an exception. If it does raise the exception of out of bounds, we output this error and tell the user, okay, the objects are not of the same size, so that they know, the user knows what's going on here. Because you can't, remember what I said, you can't try to transfer the contents of one object to another object if they're not of the same size. Impossible. You can't pour 2 liters of Coke into a 350 milliliters cup. You can't do that. They're not of the same size. You need something that's the same size as the 2 liter of Coke. That container also needs to be 2 liters because you're transferring 2 liters. Okay, we come back to node base. Yeah, this was easy, this one. The secular one, it's a bit confusing. We need to do the straightforward one. This is the linear one. So let's do the linear one. I don't know how I'm going to transfer this code though, but yeah. Okay, what I want is to remove everything that's here. Okay, I don't want to leave this. Okay, let me just leave this. Okay, I think I'll also have to, I'll also share this one. Yeah, let me just leave this and leave it like that. And then now let's, yeah, I guess I'll just have to, you see these files in the link. When you click on the video, the playlist, there's going to be a URL to the website where I've uploaded these files, the CPP and the PDF and everything. So don't worry about that. So CD documents. Okay, I was not supposed to move out. So computer science 1B 2021 memo, and clear the screen so that they can see better. So now let me create a file called code. Then I open this file with the Visual Studio Code. So if you open here, there we go. And then now I start coding. Okay, I don't want to close this terminal because I don't want to keep it directing. So hash include IO stream, right? And then int main, then return 0, right? So always the first question is going to be version 2.4, right? Always the template version, right? So let's create the template. Let's see, what do they want? Provide code for a templated node structure compatible with the depicted data structure. So you must use the right data structure. You can't create a class because there's no methods required here. You can't create a class. The only data structure that we can use is a structure. It's a record structure. Because with the record structure, you can create a new data type that works with data. If you look at this code, it works with data, values and addresses. And if you remember, pointers are they are a way for us to store addresses. So I'm gonna need a pointer. And if you check each node, right? If you separate everything, you check, if you look at it, remove the tail, remove this, and remove this first part. Each node stores a value and an address or a link to the next value. And what's the next value? It's also another node. So let's do that. And remember, it's templated. So template type name t, right? And then struct. I'm gonna call it node. because this represents each node or each circle and an arrow. That's the circle and an arrow combined. That's the node. Just that with the circle and arrow, I feel like it's a bad drawing. It's a better. It's a bad uh, analogy, but it's not. It's not too bad. It's still. It's not too far fetched, but I feel like we can do better in terms of that. So I'm gonna make it an SVG. I'm gonna call it node. Yeah, I'll just add it to the question. Yeah, I'll just add it to that document when I make the PDF. So we're gonna have this node, right? And then copy, paste. Then there we go. This is going to be our value. Then this is going to be our address, right? And then this is going to represent the head, this one. And then copy, paste. And then paste. Then paste. Okay, I don't need this part. I don't know how you, let me see. Yeah, this is what I need. Okay, this is how you go back. Okay, so I just need a few things. I just need the text, then I can do full screen. There we go. So we have our nodes like this, right? So this is going to, okay, this should be here. This should be the value for this one. This one's going to be A, right? But I feel like it's not that clear. So let's go to the text field and then increase the size to like 30 something so that it's a bit clear. Yeah, that's more like it. There we go. Then copy, paste. It's going to be B, B, and then paste. This is going to be C, and then paste again, then copy this node and have it there. Yeah, I feel like, yeah, if I zoom in like this, if I do full screen, it's good because now we can see what's going on. And then this is going to be D. Copy, paste. Okay, this is going to be D. There we go. And then each node has the address of the node after it, or the next node. There we go. There's the addresses, right? And then this is going to be the head. So this is going to have the label. Okay, it doesn't have a value. Let me not say, let me not put it there. It's not, doesn't have a value, this one. This is going to be our head, where it starts, right? And then the tail is going to be, it's going to be, it's going to be here. It's going to point to this one. So the tail is going to be here. So this is going to be the tail, like this. And then this tail, it points to this. This is our diagram. The tail points to this. But then with the head, let me see with the head. Yeah, it is an arrow like that, but with the head, let me see. With the head, I would say that with the head, it's a bit, Yeah, we could. Yeah, technically we could create it as a node, but with the head, yeah, with the head, we must store the address of the next. Or maybe let me see. We'll try to do it in a different way because the head and the tail they shouldn't necessarily be nodes themselves. They should just be pointers, right? They should just be pointers. So I'm gonna try and do it in a better way and see if we can do that. So I'm gonna put this here. There we go. There we go. So our nodes are here, and then we're gonna need another shape to represent the null pointer. So I'm gonna exit full screen, and then make this. What color can I make this? Can I just make it orange? I just want it to be a very different color. So this orange basically represents null. So this one's going to have the address to null. Then copy, paste. This is going to be null pointer, right? So that's null pointer. So we have these pointers pointing to this, the head and the tail. So what I'm going to do is, yeah, I think I kind of see it now in a simpler way how we can create this in a much simpler way. I don't know why it's doing that, but it shouldn't be. It shouldn't keep saving and saving different files. Okay, let me plug my charger because my batteries seems like it's running low now. So let's continue. So we have our nodes, right? So I think I just used, let me see. I think I'll just use type aliases. So I'm just gonna use the address, literary addresses. I won't create nodes for them. They're just gonna be pointing to those addresses as well. So if you remember, data, what is this? Pointers. You can also create a variable like this. Remember variables, whenever I say x is equal to 0, this variable is stored in memory at a specific address. So if I do the standard cout address, let's say address of x, what address will it show me? See, it's going to output an address to show you that it is stored in an address. So compile node.cpp file and then create an object file called node and execute the node. As you can see, it's in hexadecimal. So every variable, everything that you create in a computer, it's stored in a location. There's an address. That's how it keeps track of the things. Everything has its own address. So you could initialize the address of, you can create what we call a type alias. So when you create like this is what we call a type alias. So you create a variable that's gonna point to that address. It's gonna get an address for that specific value or for that object or whatever that thing is. So we call that a type alias. So instead of it getting its own address, right, it's gonna get the address of whatever I'm initializing it to, whatever the address is for that variable. So we could use it like that. I think we could use it like that. If you want to avoid having to create a new node as the head and whatnot, we could create it like that. So what I would do is I'll open this book. Mm, 1115. So let's see if, because the way I was doing it, I was just creating its own node and then points to that. So as you can see, if you see this example, right, remember there's the data and the link, the value and the address. Here it's that color which signifies that it's only the address. So, but at the end of the day, I don't know how sometimes you see here they're calling it the head. I don't know what that's supposed to mean, but yeah. So they actually made it a pointer there. So I'm not sure if that's how we should do it, or but I feel like the best way to do it would create is to create a type alias to just have the address of the head. You see what how you traverse, you set the current to the head and all of that. And the head, the way it was created, if you check the head, right, the head was created in such a way that where is it? It's a pointer, the way we did it previously. You could do that. So I feel like for now we're just gonna stick to that example. I'll show you another simpler way of using type aliases. So basically, instead of me storing it as a whole node, I'm just gonna store the address. But I think that should be fine. That it's better to do it that way. Let me see. If I do it that way, how would I update the address? Yeah, let's just use the pointers. Yeah, I think it's best to just use pointers because pointers I'm gonna be able to store the address, because a pointer is a way to store, to literally store the address. If I use type alias, basically this thing int head, and then it points to the first node. Then I haven't stored the address. I haven't stored it. I'm only storing the value. That's a problem. So let's maintain exactly the way we're doing it. Remember that the usual way is to have some value here, then you're gonna have the node or the address of the next node, like this. Because remember this type, whatever value that you have is going to be stored inside a specific address. So this node is going to be stored into a specific address. And in order for us to get the address of that node, I'm going to make it a pointer. So I'm going to say node pointer, point to the next. But then remember, this is a generic point. This is a generic node that we're supposed to create. We are creating a generic node. So since I'm creating a generic node, I'm going to change where there's int and put a t there, and then state the node. Remember, whenever you make something generic, whenever I use the name of that generic thing, you must pass, you must put next to it the less than symbol and the type or t variable, followed by the greater than symbol, to specify that it expects a type in between those two symbols, the less than and greater than symbol. Sorry about that. Network, there was network issue. Let's continue where we left off. So I need to have a head and a tail. And as you can see, it's made up of what? Nodes and characters. It's of type char. So let's see. And they always flip it around. You can see, you'll see, they always ask different questions, deleting, whatnot. Let's see, provide code for inserting a node, the value E at the end. So it's E at the end, right? So remember that by default, whenever I'm coding, right, I don't have this code. I don't have the links to these values. I have to create them from scratch. So that's what I'm going to do. I'm going to create them from scratch, add the value so that we see after adding E whether it did add the E or not. So I'm going to have a tail and so yeah, I'm going to have this tail and the head. Yeah, tail and the head, right? Then I'm going to create new nodes for both. Okay, no, what am I saying? Create new nodes. So new node type char. Then for the tail, got a new node type char. Right? Yes. And then we have our new nodes, right? They're in existence, right? So when I say new node, remember what I said. It's literally just building this. Literally just building this node. Yeah. Remember, this is the node. That's what the new does. So I have this new header and a new tail, this new node. But then remember, this node is not supposed to store any value. It just stores the address. So we're going to use that to store the address. But then remember, this moment we don't have any new nodes, right? So I'm going to create, remember at the moment, they're going to have these addresses, right? I don't have to worry about the next. What I could do, right? I could do this. I shouldn't do it, but it's not necessary. It's not necessary, but I could do this and set the next point to nothing because there's nothing at this moment. And then heads, what is this? Tails next. Tails next to point to also nothing because there's nothing at the moment. I haven't added anything. And then I'll update them as soon as I add the value. So add or insert character A. So I'm going to create a node of type char called A new node like this type char the character. And then now we get to the steps, right? So the first step is you can organize it in what way, just to make sure you do all of the steps. So I can set the value first, just give it a value. The value is going to be the character A, right? As denoted by the small a. It's going to be the character A, and then A is next, right? It should point to null pointer because at this moment is the only node, so it should point to nothing. But then the head and the tail need to be updated, right? So I need to update the head and the tail. So let's sort of like demonstrate how this is going to be shown in the diagram, right? So let me delete this. So at the moment this is what we had. I want to show it step by step so that you guys can understand. This part, new node, let's demonstrate that. It created a new node. Delete this link here. Created a, come on. Created a new node, this one here, like this, called head. That's the new node. That's the name. It's called head. That's what it did here. This line that I've highlighted here. And then it set the nodes next to point to now because there's nothing at the moment. So nodes next, which is this one, points to null, right? Because there's nothing at the moment. So there's nothing at the moment. And then that the next line creates a tail, a new node, then give it a label called tail. So it's going to create this new node here. Let me just copy everything here. Then obviously the tail is going to be somewhere here towards the end, right? So I'm just going to put it there towards the end. So tail, it's going to have the label tail. And that's what it did. It created this new node with that label tail. Then now I set the tails next to now pointer. So I go here and I set this next to point to now point. So it also points to nothing, right? Because there's no node at the moment. You see, they're both pointing to nothing. There's nothing that is pointing to. There's no nodes at the moment. So let me just delete this. So this is what we had, that line so far here. That's what I was doing. I was creating this point to now, right? Let's do it step by step so that you understand what's going on. And then this part, create the node and give it a label A, the small letter A. So let's do the very same thing. I copy this, copy, let's put it there. And then we should have the label small a, right? I'm gonna put the labels at the top for these nodes so that when I try to point to them, I won't have any issues. So it's gonna have that label small a, right? Then let's shift it. There we go. So there's that node A, right? And then that's that line that I've highlighted. That's the only thing it does, that one line. Then now it sets its value to be the character A. So it goes here. It's just that in my mind I can picture it. I have a vivid imagination of what's going on. So that's why I'm able to write these things properly, step by step, because I know what's going on. I can picture these diagrams. So as you can see, that's perfect. This is the perfect zoom. So as you can see, now it is the value A. Remember the blue box I said represents our value, and then this pink or reddish box represents the address to the next node. So that's the value. And then set A is next to point to now pointer, right? So now A is next points to null pointer. Let me do this. Come on. It points to null, right? Because now it's the last node. It's the first and the last node, obviously. So now what we need to change is this node, the head. I need to update its next to point to A. It should no longer point to there now. So let's do that. So set heads, because now I have the first node. So heads next should point to the address of A. Because remember what a pointer is. A pointer stores an address. The variable without the pointer is the address itself. So if I write only A here, I'm getting the address of A. If I write pointer A, I'm pointing to the address, or I am going to the address. So what this means, it means the address of A. So set heads next to be the address of A. And if you look at heads next, right, it's also a pointer, but I'm only accessing next. I'm not saying heads pointer next value. I'm not saying it's a value. No, I'm not doing that. I'm setting next. I'm just only using the variable itself next without that pointer. If I use it without the pointer, it means I'm referring to the address of this node. Set the next node to the address of A. So this line, what it does now, it goes here. What is the address heads next? It's this one. So it updates it. So I remove here and then it updates it. It now points to this node A, the address of A. So, okay, it doesn't have to be, let me see, let me do this. Let's structure it in the right way. Okay, still fine here. Okay, let me put it like this here. Somewhere here, like this, yeah. So this is going to point to this node, like this, where that node A is located in. And then now, remember that our tail it points to the last node. So now we also need to update the tail to point to this first node, because that's the only node that's there. It's the first and the last. So both the header and the tail should point to the same node. So tails next, point to A. That's simple. And then I cut this, and then I take this nodes next. It also points here because this is the first and last node. So now they both pointing to the same node. You'll see that it will change as I add new values. So this should be moved a bit up in alignment to this. There we go. So now this is what's happening. This is what we currently have. All of the code that I've written so far, that's the diagram that I have. All of this code, that's the diagram that I have. So now let's add or insert character B, right? So in order to insert the character B, we have to follow the same procedure. I have to create a new node like this in memory first. There's the new node and give it a label. So create a new node. The label is going to be E, of the new node. So that's what this one line of code does. It builds this new node. And then it has a label B, right? So I'm just going to give it a label B. Top. So I'm just going to put it here because eventually I'm going to edit there at the top. So B, right? Small letter B. And cut all of this, put it somewhere. Okay, put it. Okay, it's fine. Let's leave it down here. It's called B, right? Let's leave it down here. There's no pointers. There's nothing that is pointing to, no value, no nothing. Let's add a value, right? Let's give it a value. So B's value and to be character B. So what this line of code does, it looks for the container that's called the node that's called B, with that label B, and then it gives it a value of character B. So it comes here, it gives it an uppercase character of B. And now we need to update pointers. Now my first node is no longer the only node. So I need to update its next to now point to this new node, right? Let's start with that. So the first pointer, which is A's next should now point to what? The address of B. So we go back here. This node this next that was pointed to now pointer previously. It now points to this new node. So I need to move it here because it's now part of the family. So I point to it like this. So this is what we have so far. There we go. So now it's pointing to this. But then I also need to update my tail because this is no longer the last term. This is now the new term. And I also need to update this next address to point there. In whatever order you want to do it, it's fine. Because I can start with this one to point there and then change this to there. Or I can start with this tail to point to this and then this points to that. The only time it's crucial or it's important which order you use is when you're deleting. Because if you delete something without deleting its pointer first, like the pointers of it, the order is very important. We're going to get to that. So I've inserted this. Now I want to I'm going to start with setting B's next to point to now. So let's look at B. B is next should point null pointer. So what this line of code does, it's going to go here and take this next address and make it point to null like this. So you see, I've joined it. It's part of the family now. But then now I need to update the tail, right? I need to update the tail. So this address, the tail's next address that is pointing to, it should no longer point to A. You should point to B, to B's address, because B is now the last element. It's now the tail. So tail's next should now point to B, right? Yeah, that's fine. Yeah, it should now point to B. So tails next should now point to B. So this is what happens. It's going to come here and take this and point there, because now this is now my tail. There we go. There's the diagram that I have so far. And then um, okay, I'll just save it once, because if I keep saving it, it just updates and adds a one. So I'll just save it. I'll just save all of the whole diagram once I'm done. And then now we do the exact same thing over and over and over, right? So now you see the flow. So let me insert C. So I need to create the new node first. Get a label pointer C. Because remember the nodes that I have, they need to work with addresses. So I'm going to make them pointers. So node char. Then set C's value. Let's start with the value first. It's going to be the character uppercase C, upper letter case C. And then now B is no longer the last element. So it shouldn't point to null anymore. So okay, I feel like I shouldn't be lazy. Let me just do it, man. Let me just draw the thing step by step. The videos might be a bit long, but as long as you guys understand. So I'm gonna have this new node, right? And have the label C. Let us see. That's what it's called. That's the label. It's gonna be at the top. So that when I add it here to this diagram, it makes sense. So there's the label, right? So far what I've drawn, it's only this line. So we did that. Then now set the value of the node with the label C to be uppercase letter C. So set its value. Remember the blue part in our example, we're gonna use the blue part as the value part. Set the value to be C. There we go. Now I need to update my B's next. It's no longer the last element, it should now point to this new node. So I should change this pointer. So this is what I'm trying to do. I'm gonna take this. No, okay, there we go. So I should change this and make it point to this new node like this, right? But then if you see, if I try doing it this way, it's going to become a problem. So yeah, so I'm just going to make this new node from here to point to this one like this. That's what I'm going to try to do. So let's do that. And which node, what label is it? It's a B. It's the one with the small letter B. So the label with the small letter B, get the node and then get that node's next and make it point to the address of C. So now this line, what it does, it's going to come here. I'm just going to move this node up so that it's easier to point to. What's going to happen is going to go to B, take B's next and make it point to C like this. So this is what we have so far. But then remember now B is no longer the last element. I have to update my tail and I have to update the C's next to point to null pointer. All of that in whatever order you want here doesn't really matter, especially after you've pointed this node to the new node. The order doesn't matter. So now let's point. I'm just going to always start with this one. Make this new node point to null pointer. I'm always going to start with that one. So the new node's next, which is C is next, should point to null pointer like this. So now the arrow for nodes next points to null pointer. And then now I need to update this arrow for the tail to point to this one, because this C is the new tail. Remember, the tail is just the last element. So this is what I want to accomplish. Take all of this. Take all of this. And then make it point to this new node. That's what I want to achieve, but I need to write it down first before I point. So what I'm going to do is tails next to point to a new node, which is C. There we go. So this is going to do this. There's the new node that we've added. So this is how the diagram would look. Then this would look like this. I think let me shift it to this side like this. And then yeah, I want it to be straight. And then this node, yeah, the head for now is always going to point to the first node. The only thing that's going to change is the tail. So far this is the diagram that we have. Every pointer is pointing to the right location. Everything is fine. There's no issues here. Then we add the last element, which is D, the node with the value with the character D. So char and then pointer D is equal to new node of type char. There we go. And then let's build that node. So what it did, that line of code that I wrote, what it did, creates the new node like this called, give it a label. How am I going to refer it to it is have that label D, let small letter D there. That's how I'll know that I'm referring to that node. So far, this is what we've created. It's empty. There's no value. There's no next. There's no address that is pointing to. It's next. And you see, there's not pointing to anything. So now let's update its value. So I use the label, which is the D. And then I say it's equal to what's no, not its next, its value is equal to the letter D. So now when you go back to our diagram, this blue box, remember the blue box represents our value, and then the red one represents our address, the next address, the address of the next node. So now this is what I've done. I've given it the value. So now we need to update the pointers now. Let's update the pointers. So I'm always going to start with this one, this new node, make it point to this. That's the best thing to do. Make the new node point to this before you update any other thing. So I remove this pointer to this because now C is no longer the last element. I make it point to this new node. So there we go. And then copy everything and then I move it here like this. So now I need to update C's next to point to the location of D or the address of D. So C's next, make it point to the address of D, which is just the variable D without the pointer. It demonstrate, if you remember, pointers, when you output the variable without the pointer, it just outputs the address. So I'm changing the address here. So now it points to D like this. So that's what we have now. Then I also need to update this tail. So I'm going to create it like this. There we go. So I need to update tail's pointer, but then I need to start with updating this one. I'm just going to update this one to point to null pointer. So D is next should point to null pointer. So D is next should point to null pointer. So when you go back here, D is next is going to go here and point to null pointer. There we go. And then now we need to update the tail to point to D. D is the tail is next should point to D. So this is what's going to happen. Point to D like this. Here's the node. So now we have the node as shown per, per, per illustration. This is the node that we have now. We have that null pointer and the tail and the head. So I have the head and the tail. So now if I want to insert a node value at the end of the data structure, how would I do that? You've seen how I've been coding. It's exactly the same procedure. But before we do that, let me output my node before. Say out node for inserting character E, right? And that in space and then end line. That's going to be my node before, right? Remember how we do it. I create a node that points to the head. Current that starts to the heads. But then remember, it starts at the heads next. I want the address that the heads next is storing, which is the address of the first element. That's perfect. And then I'm going to say while the current address is not pointing to null pointer. I'm still not at the end. So the current address is not pointing to null pointer. Then what should happen? I should also check if the currents next. Remember, I wanted to now I want okay, now it's proper, it's not a secular list. So now I can output it like this. Have arrows like this, sort of like how it's shown in the diagram. So I want it to be like this. So what I'm going to do is I'm going to keep outputting this combination, a value and an arrow. And then the next iteration, output a value and an arrow. And then the next iteration, output a value and an arrow. But then once I've reached the last element, which is D, how do I know I've reached the last element? If it's next, if we check the diagram, if it's next is pointed to null pointer, then I know this is the last element. Or if it's the tail, or if it's the tail, or if or if I'm pointing to the tail, yeah, you can also use the tail. So let me see. As long as it's not equal to null, yeah, as long as it's not equal to null point. So I can use the tail. I can just check if I'm not equal to the tail, then because the tail stores the address of the last element. If I'm not equal to the tail, now it makes it simpler. If I'm not equal to the tail, then don't print the combination of a value and an arrow. But the moment I become equal to the tail, it means I'm at the last element. Don't print the arrow. Don't print that combination value and arrow. Only print the value. So it's only going to print D, so that it doesn't look weird, because now it's going to make it point to show like it's pointing. You see, it doesn't make any sense. We can't show the character now. We can't draw now to show it there. So if current not equal to a tail, then I should output that combination. So see out the current's value, right, followed by the arrow like this. And then else it means that I am equal to the tail, because I said here, if I'm not equal to the tail, output this combination. Now, if I am at the tail, I just output the value. I just output the value like this. And then at the end of the day, I need to output a new line character like this. So this is before, right? And we can also show after. And I just have to copy and paste the code. So this is what, so far, all of this code that I've written is not to answer the question. I'm just showing you how it was looking before we try, how it looks before we try to make any changes. Remember that they don't give you the code. They don't give you like everything, how it was inserted and everything. So yeah. Okay, something is not right here. What did I do? Oh, I see. I forgot to move to the next to the next node. So I forgot to update my current to point to the next. So basically, I just forgot to say I plus plus in a way. That's why it's outputting the same value A. So cd document LSCD Computer Science 1B 2021 memo and LS. So I'm gonna say G++ exam underscore tab minus O exam and dot forward slash exam. Okay, I'm not running the right thing here. That's why. I'm supposed to run the, let me see, node, right? Yeah, it's node. So I'm supposed to run node.cpp minus O forward slash node. Yeah, there we go. There's the node. Before inserting, okay, it's not how I planned it out to be. Okay, let's just rephrase it in this way. Let me say if current next is not equals to null pointer. I feel like that's more accurate. Current values next. Let's say look at my current value. Let's say I'm currently at D. If it's next, you see it's next is pointing to what? Null pointer. Therefore, I know this is the last node. Therefore, I won't output that arrow after it. So as long as I'm not, the current next address is not pointing to now, then I know I'm not at the end. I'm not at the last node. Therefore, just output that value, current values node, the current node's value and an arrow. Else, if I am at the last node, don't just output the value, don't output the arrow. So let me save these changes and then run it again. Here we go. There's the correct output. A to B, A points to B, B points to C, C points to D, and then C doesn't point to anything. So we are good to go. We are good to go. So let's answer a question, right? Because here I was just demonstrating how we can do this. Well, I wanted to have the node first before we attempt the question, because we can't just be writing code and you guys don't see whether this thing is indeed working or not. You need to see if it's really indeed working or not. So how do we insert? The way we've been inserting this whole time. You see, the reason why I like demonstrating like this, you end up answering questions before you get to the question. So how do we insert E at the end? If you check here, insert the value E at the end of the data structure. So after D, insert the value E. It's simple. The first step is to create the new node. Copy, paste. So this is the first step. Let me paste again. So this is the first step. I need to create the new node here. That new node, then give it a label. In our case, we're inserting the value E. So I'm going to give it the label small e. Yes. So that's what I'm going to write now. So create a new node. Give it a label E. Create a new node like this. So now we have the new node, it's ready. We have the memory now. We've allocated memory enough for a node, for a value and an address of the next element of the next node. We have that memory and it is labeled small e. So we are ready now. Let's set its value to the letter E, because if you check here, we want to insert E at the end. So I need to update its value to be E. So the label E's value should be the uppercase letter E. So we go to the diagram and then this is what happens. It stores the uppercase letter E here. Now we have the value now. Now we are left with pointers, dereferencing and changing addresses and all of that. So now I need to update these. The element that I previously thought was the last element. I need to update its next to no longer point to null pointer because it's no longer the last element. It should now point to the new node that I've created. So I'm going to delete that link there. And then, okay. shift this to a bit that side, and then copy all of this here. So I need to update this D's address, or this node with the label small letter D, to point to this label, of which the small letter E. So it's very simple. D is next, now be updated to be the address of E. Basically, the node with the E label. So this is what's happened. This is what's happening in memory. It takes this point and points it here. There we go. Now I need to update E, the new node, now to now point to now, because that's the last element now. So E is next, should now point now, because that's the last node now. If you check this, it's going to point to the last node, to now pointer to represent that it is the what? The last node. So now the tail, it should point to the last node. So the tail should now point to the last node. So which is E. So I need to update it. It's no longer D. Because remember, D was the previously, this was the node that we previously thought was the last node. But now we've added a new node. So I need to update the pointer for the address that the tail is pointing to now point to the new node. So tails next now point to E, new node. So now when I go back here, it's going to update the tails next to now point to this new node, like this. And then there we go. It's perfect. We've inserted the diagram. So I'm just gonna save this, right? And then go to where it's located. And then I'm gonna call this, I'm gonna rename it and call it insert E, right? I'm gonna call it insert E. So how would it look when we insert E, so that I don't lose track of the shapes, because we have to delete something here. I think we're supposed to delete. So provide code for deleting the entire data structure. Yeah, you have to delete the entire data structure. So we have to change pointers here to delete the whole thing. So let's output it after changing. So this was the before. So let's output it now after changing. So I'm just going to copy that code that I wrote for outputting. Then I put it immediately after inserting. And then I'm going to call it after setting. Remember, we have the current variable. I don't need to redeclare it again. I just update its address to start from the head again. That's all I have to do. And then since this command's already saved, I'm just gonna run them. There we go. So before inserting E, this is how it looked. And then after inserting E, there's E at the end now. If you understand the diagrams, you see you won't face any errors. You see, so far, there's no errors here because I understand what I'm doing. I'm drawing the diagram on each step to understand which pointers, where should it point to, which nodes next should it point to, on all of that. It's very important to use diagrams. If you use diagrams, you make things easier for yourself. So let's try to delete the entire, right? So delete the entire linked list, right? Which is basically question 2.6, right? This is 2.5, 2.6. So for 2.5, right? Remember, this is only the code you need to write. Me, I'm just writing here so that you can see. So I would say the code ends here. I'm only writing this so that you can see where it ends. It ends here. This part is just for me displaying the node. So this part is just display the node after setting character E. That's all I'm doing there. So the actual answer is here. So answer for this one, I'm just gonna do this. Just gonna say this question answer starts here. Because I know some people might be confused, like, okay, well, I have to rewrite all of this code. You don't have to. I'm just doing this so that it makes it easier for you guys to see, so that we have the actual output, how the node looks. Answer ends here. So the moment you reach here, you don't, that's where the answer ends. So everything between here, that's the answer. The rest is not the answer. Just keep that in mind. And then this is the answer for 2.4. So yeah, when you go through the code, just check it out. You can run it and play around. Yeah, you can do all of that. Try to change and do all of that. Yeah. So delete entire linked list. So how would we delete the linked list? So the way we delete linked list, right? Remember we have memory allocated, right? So the first thing that we do is to delete the memory for each node, deallocate using the delete keyword. And then we set the pointers to point to null. That's the most efficient way that I can see, that I can, yeah, that's the most efficient way to delete. Because remember why am I saying we should delete? There's the keyword new here. Remember, every new is accompanied by a delete operand or delete operator. So what I'm going to say is delete, and we must make sure every pointer points to null. Remember how we delete, you just delete that object. So delete A, delete B, delete C, delete D, delete E, then make A point to null, then make B point to null, then make C point to null, and then make D point to null, and then make E point to null. Make it point to null pointer. So what does the delete keyword do? The delete keyword, it deletes the memory that it had. So this box, it's like it literally deletes it like this. But then remember now this label is still pointing. So let me just show you how it deletes. So let's delete this. But then remember these labels are still, they still have pointers to them. So delete this again. And then we have this label. Okay, let me do this so that I can move the pointer around like this. So that's what the delete does. That's what I'm doing when I say delete. So I'm going to delete this. So this is how it's going to look in memory, right? And then okay, I can delete this one. Remember, E was always pointing to null pointer, right? I mean, technically with E, we don't have to make it point to we don't have to change the pointer for E because it's already pointing to null pointer. Technically, just keep that in mind. You see, remember E is next. Oh, okay, it's fine. E is next. That was E is next, not E. Yeah, okay, it's fine. Yeah, it's fine. Or you have to do this. Yeah, you have to do this. Yeah, definitely you have to do all of that. And then we also need to delete the tail's memory. Yeah, there's a lot of deletes here. Don't forget to delete all of them. So we have to delete the tail, delete the head. There we go. And then remember the tail and the head, right? They had memory. They had an address that they were pointing to. So I have to also set them to null pointer, but there's nothing to point to now. So this is how I would approach it. I don't know how they approached it, but this is how I would approach it. Because everything now needs to change. You see, now everything needs to point to what? Null pointer. Basically nothing. Remember this orange circle, it just basically means it's nothing. Remember the head, we also deleted this thing, delete this memory. And then, okay, we just delete and have this here. And then make it point to null. And then this one, E, remember everything now should now point to null. So it's like now they're in agreement that, okay, we should all point to nothing. You see, this is very important. If you don't point to nothing, you're going to try to, what if you try to reuse the same memory by mistake and there's no memory anymore? So if you set it to now, it's going to show you an error that makes sense, the segmentation fault error. Segmentation fault error, you now understand what it means, right? It means that you're trying to access a pointer that's non-existent. It's a null pointer. So now you'd know, oh, okay, this pointer is no longer accessible. So now you see everything points to null. I've deleted and everything points to null. So this is, I'm going to rename this to after deletion. Deleting, that's how it's going to look. So that's for deleting the entire data structure. Yeah, that's all you have to do there. Make sure you delete the memory that you've allocated first, then make these pointers all point to null. Remember the pointers, the pointers themselves, the addresses themselves, they were pointing to something. They had their own memory address, right? Also make them point to null pointer. You could also, I think something is missing here. Let me see. If I'm not mistaken, there's a lot of things you actually have to change, because I'm also thinking about the next. Because so far, the code that I wrote, it's only the actual addresses of the variable themselves in memory, not their the next address that they are pointing to. So I think you'd also, on top of this, you'd also have to add the lines dot next. Dot next is equals to null pointer. Dot next is equals to null pointer. Dot next is equals to null pointer. It's a lot of things to remember, but let's just double check. I'm not sure if it's in the textbook though. If 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 they did it exactly the way I did it, let's see. Hmm. Yeah, okay. To delete, you just change the pointers and whatnot. Okay, I think you just delete. You don't necessarily have to worry about the next. Oh, yeah, I think it makes sense. I think when you say delete, right, you are deleting everything, even the next the next address. But let's just double check. I want to see if there is. Set it to null pointer. Okay, destroy the list. Okay, so yeah, this is okay. This is actually how they want you to do it. Okay, so let's do it this way. Let's do it that way. So let's use a while loop. We could technically we could it's still fine this way, but let's just also let's do it using a while loop. Maybe they want it to be that way. So what I'm going to say, I'm going to say current is equals to the heads next is the address of the first element, right? So while current not equals to null pointer, right? It's not equals to null pointer. Obviously we must move on to the next element. So it's equals to current next. Then we're gonna need to keep track of the a temporary node. So temp, I'm gonna set it to current because I don't want to. What I'm trying to avoid is having to delete this, whereas it's still whereas the still it was still pointing to the next node, and the next node is not deleted. So what I'm going to do is I'm going to create a pointer and take the address of the current, right? And then delete that temp object, right? That memory that was allocated, right? And then this should be fine. But I feel like it's exactly the same way that I did it, but this is a sort of like a simpler, shorter way of doing it instead of having to do it manually one by one. So you just delete the current object. So what happens is that, remember, it starts at A, then there's B, there's C, there's D, there's E, right? So it starts at A, the address of A, which is stored as the heads next. So I store A into a temporary variable so that I don't lose this pointer, because I still need to point to the next. So I use this temp, and then after storing it into this temp, I delete, right? I store that address, I delete the memory allocated at that address. So we have basically so far we haven't deleted anything. We just deleted the memory. We haven't changed the pointers because so I feel like I think maybe I don't want I don't want to be taking any chances here. So far, what we deleted is the memories that each node had been allocated to. But then now I need to change. I need to make them point to now so that I don't have dangling pointers. Dangling pointers is just pointers sitting there, not pointing. Like not necessarily pointing, but it's just pointing, but it's pointing to something that's it's not even now point, it's just dangling, it's just sitting there. So at least the least you can do is make it point to now. So what you can do is once you've done deleting the memory, because if I can't set the next, you see one thing that I need to avoid, I can't set the next address to point now pointer, because if I do that, then I'm gonna lose track of my pointer. If I set the next node for A to point to now, this is what happens, it disappears. I lose track of all of these nodes. Now I can't delete them, I can't point to them. So that's why they did it like this. You have to start by deleting the memory first, then we can set the pointers. So with the pointers next, remember there's also the heads memory. There's a lot of memory that we have to delete. So at the end of the day, okay, it kind of makes the code a bit shorter to be honest, but yeah. So we must also not forget to delete the heads memory and delete the tails memory. Because okay, for us, in the approach that we took, right? we took a node by using a pointer because we wanted to store the address, and then the tail we wanted to store the address. So we also need to deallocate because pointers. Remember, with the pointers that we have, we're working with the heap, so we need to delete their memory first, and then we need to update all of their next addresses. It is a lot of. To be honest, this is it's still going to be a lot. Yeah, still going to be a lot because I want to make sure there's no issues here. So heads next, right, should point to now pointer. So now point heads next is not pointing to anything. Let me just see if it won't give me issues. If it gives me issues here, let me save. This means that you don't need to do more than just deleting. You could just leave it like this. Yeah. So it gives you a segmentation fault. So you don't have to worry about the nexts. So just delete memory. That's it. Just wanted to verify that. Segmentation fault where exactly? It's still okay. It's still the error is still there. Mm, it's giving me segmentation fault. Let me see. Oh, they don't. The way they did it is weird, though. Yeah, it's weird. Okay, let me see what line exactly is causing this error. Okay, so these are not the lines. So so let me see if I take the address of the current, right? So I delete that memory. Hmm. Interesting. I see. I think I kind of see what's going on now. Because if I delete the memory here, and then I still want to use that variable, but there's no memory allocated to it anymore. Obviously, it's going to give me a segmentation fault. Basically, I'm trying to access a memory that doesn't exist because it's been deleted. So if I just move this one here, deleting part, how are we supposed to delete it using their own method? Yeah, how are you supposed to delete it using their own method though? Hmm. Oh, wait. I need to. I think I need to start by. Okay, it's still fine. I store the current and then I delete. Blah, blah, blah. Okay. Okay, it's back. The network is back. I'm trying to check here how they want you to do it. Okay, we don't want to be working with what is this? Okay, to traverse, we got that right. We don't have issues with traversing. Current info, blah, blah, blah. Okay, traversing, inserting, changing pointers and addresses, blah, blah, blah. Insertion, deletion, right? So how do you delete? So you have a current pointer. Let me see. Then Q is equals to P. Must keep a pointer to the node to be able to delete its memory. Okay, so this is how you can, this is how they're deleting it. So we create new pointers, right? Or new nodes to keep track of where we currently are so that you don't lose the pointer. Oh, okay. No, I see. This one is to delete like a specific node. So you can create a pointer and then, so for example, let's say I want to delete the first node, right? I can create a pointer and make it point to the node that this first pointer is pointing to. Then I delete the memory for that pointer, the first node, and then I redirect its pointer to point to now. I still have access to this pointer. Then I update the heads next to point to whatever this address this new pointer is pointing to. So that's how you delete it. So how do you delete an entire one? Okay, now it seems like they want us to, okay, now they're introducing classes. So I think this was 2021. 2021, it wasn't playing. It meant it meant serious business. So let's see. I think I kind of have an idea of how I'm going to delete. So I'm going to create a temporary variable, right? Call it let's call it, I'm going to have a current, right? And then current variable and temp, two variables. Temp, what temp is going to do, it's going to start pointing to the node after the first one. So that I don't lose this address. Then I delete this node. Okay, the head, yeah, I can also delete, doesn't really matter. So I can delete this. I can delete this node, the head, and this. Okay, yeah, I can delete that. So remember what you can do, right? Before we do anything, the beginning, we can just delete head and delete tail. Because remember the tails and the head, it's just pointing to the first and last node. And oh, okay, yeah, okay. Let me see. Yeah, I must not mess this up. Okay, yeah. No. I can't do that. I can't mess this up because remember I need to get the address of the first node first. After getting the address, okay, yeah, I think it's safe to delete after getting the address here. I have stored the address in here, so I have the address. So now I can just delete head. Then I'm done with the head. And then current stores the first address, right? So now what I'm going to do is I need to create a temporary node, temp I feel like this temp is gonna start by storing the currents next. Basically the second element, right? It's gonna point to the address of the second element. Then, with that being said, let me think. Because what I'm thinking is like you have these values, right? A, B, C, D, this. So I create a pointer that points to, for example, I call it, let's just use T. So it's gonna start pointing at B, the second element, so that I don't lose the address, right? Now the question is, how am I going to delete this node? Because it's the current, right? So current, let me see. I think I have an idea now. So the I think what temp should do is it should store the address of the next address, right? Then I'll delete current here. See, let me think about this. Will it work? Let's see. Always points to the next address and then delete that memory. As long as it's not equals to pointer, so we don't have to worry about accessing pointer. Let me see. Okay, I deleted twice. Okay, I like how it's explaining. It says freed, so you try to delete more than once. It can be this is a very tricky question because I didn't see it in slides. How are you going to delete everything? So let's look at the diagram. So this is the diagram. This is what we want to achieve at the end, right? So let me put back this, right? I think I can use the head because remember the head points to the first node, right? I can create current to point to the address that head is currently pointing to. And then I delete the current memory here. I delete the current memory. Okay, it's gonna be a very tricky one, this one. Because I want it to be able to like come here and do this and delete. But then before deleting, I must move this to that side. So let's try and demonstrate it here. So what do I want to do? I want to move this to here, to the next element. I want to move it to the next element. And make it point here. So now I don't lose the pointer, and then I delete the previously allocated memory. The current memory, right? So let me think. So let's see. So what I want, right? This is what I want to achieve. I want to store current into temp, right? Current. And then before I delete, I move this pointer from the first element to the next element because I don't want to lose the pointer. So let's move that. So current, move that to next element, next element like this. And then now pointing to this, right? Okay, remember head, it's not necessarily going to be head, it's going to be current because I changed, remember that the current points to whatever address head the head is pointing to. So that's why I'm changing it to current. So it's gonna do this, and then after doing this, then it's safe for me to delete this. It's safe for me to do this and delete. But then also, okay, when I delete this, I think it should also delete the pointer. It should delete the pointer. So I'm just gonna delete temp, right? Because that's the previous value, previous node. And let's run it again. Yeah, so yeah, this is fine. So yeah, it compiles perfectly fine. So yeah, that's the formula that you're gonna use to delete. I think they actually did the same thing, just that I wasn't really paying, I was really understanding their code. Uh, let's see, let's double check the nodes. Yeah, they did the exact same thing. I just happened to figure it out on my own by just looking at the nodes. So what's going to happen is I'm going to keep updating the current to point to the next node. So it's going to do this point here. So now I don't lose track of this current node that I'm in, the pointer. Then it's going to delete this. Bam, it deletes. And then update this pointer again to move to the next node. And then delete the node that I had previously, which is going to be stored inside temp. And then it keeps doing that. And I said while current is not equals to now. Remember, now current is going to store, is going to point to now after moving to the next. It's going to point to now. At some point, it's going to point to now. You see, so current is going to be fine. It's going to be pointing to now. We could technically also just delete it, but then let's not also forget this pointer. Let's not also forget this tail. Remember, this tail at the end of the day is pointing here. And I don't really have to worry about the tail. I actually should have deleted it the moment I delete this one. Delete the tail. Yeah, shouldn't forget to delete the tail. There we go, compiling fine. And then now remember that temp, okay, temp, it's fine. We haven't allocated memory for it. But remember current. If you go to current, where's the current node? Okay, they didn't actually ask you to delete current or worry about current, but if you look at current, right? Oh no, current is not allocated, it just stores an address, so we don't have to delete current. And at the end of the day, current is going to point to now. Because remember, I always I take the temporary value and then store the current, create a temp and store it inside, take the current value and store it inside a temporary variable, move current to the next point, to point to the next pointer, then delete that temporary node that I had. So yeah, this is how you delete to delete the entire list, the entire linked list. I'm gonna see you in the next session. Yeah, the video happened to be too long this time around, but yeah, see you in the next session.